Dr. R. Sugurat Samuel is working as professor in physics in SRM University, Chennai. He is also training students for IIT JEE, AIEEE, and BITSAT. He has more than 16 years of academic experience both in teaching and research. He has published a book titled The Complete Handbook of Bachelor of Electronic Science Practicals. It is prescribed book in the syllabus for BSc Electronic Science by University of Madras. He has attended and presented papers in several national and international conferences and conducted many training programs and workshops. He has experience in both regular classroom teaching and also online teaching. His research areas are ultrasonics, polymers, crystal growth, and photovoltaic systems.
Welcome to UGC lecture series on Applied Sciences Electronics. We have been listening to a series of lectures on the subject Electricity and Basic Electronics for the BSc Electronic Sciences degree program. This is the first paper in the first semester. This lecture is the 46th lecture in the series. In the last lecture, we have discussed about the frequency response of a common emitter transistor. It was also called a single stage amplifier. We have seen the factual information about the frequency response of the amplifier. We have not taken up the reasons for the behavior of the amplifier as far as its frequency response is concerned. We just learned certain new terms like the lower cutoff frequency, upper cutoff frequency, and the bandwidth, etc. And what is the trend of the frequency response curve for the low frequency range and the mid frequency range and the high frequency range. And we reserved the reason for such a behavior of the transistor for this lecture. So, in this lecture, we will find out why a transistor has that kind of frequency response. And along with that, we need to learn one more important factor, that is the reason for taking the off power gain line. Why do we take the off power gain line for finding the bandwidth in the case of frequency response curve. So, let us see today's session outline before we start today's topic. In this session, we are going to see the single stage CE amplifier, the reason for frequency response and the reason for off power gain line. We could recall to our mind the response curve that we get for the single stage amplifier. In the last lecture, I have shown you the frequency response curve, because today's lecture is also in the continuation of the last lecture. Let us recall to our mind the frequency response curve by having a look at the frequency response curve. We should remember that the PN junctions in the transistor act as capacitors because of the charge accumulation across the junctions. In BJT, the capacitance across the BE junction is the BE junction capacitance, and CBC is the base collector junction capacitance for the output to input capacitance. The reason we need to find out for the frequency response, in the last lecture I have shown you the frequency response curve. The lower region, the frequency, the amplification factor or the gain, voltage gain was just increasing. In the mid frequency it was constant, and in the high frequency it was again falling as the frequency increases. This is because of the capacitance effect. As just we have seen, the capacitance effect that we have in the case of a PN junction. We have two PN junctions in the transistor. So, the two junctions do act as the two capacitors. In one of the earlier lectures, we have come across this topic, how a PN junction could act as a capacitor. When we learnt about the diode, we had this point discussed elaborately. Even we could vary the capacitance value by changing the doping and maintaining the reverse voltage across the, by changing the reverse voltage across the PN junction. This has the application here. So, we have two capacitance as I just have read out. Let us have a look at the two capacitors that are considered across the two junctions. Let us have a look at the capacitors. And this is a typical transistor. The arrow mark shows it is the emitter, and this is base, and this terminal is the collector. And there are two junctions, the emitter base junction and the collector base junction, and this is the BE junction capacitance, and here it is CB junction capacitance. There are two such capacitors, and how the signal is getting amplified with the phase reversal is depicted here. And when we give a sinusoidal wave of this trend and we get an amplified wave with a phase reversal, when we give sine wave, we get a minus sine wave here. And of course, here also in the emitter follower, there is no change in the phase, but a little lesser amplitude we are getting. So, this gives us an idea how do we have to consider the capacitors across the two junctions. When the input signal is varying and also the bias voltage is maintained, there is a particular capacitance existing across the two capacitors that we have considered. What about their effect? When we connect the resistors to the different terminals, we will have an RC combination, resistance and capacitance combination. We call that combination as a filter, which is very reactive to the AC. It would sometimes allow the low frequency to flow and sometimes allow the high frequency to flow, blocking the respective other frequencies. This we learnt in the case of filter circuits, how an RC circuit combination with a diode could act as a filter circuit. This we learnt in the case of a regulated power supply topic. So, here also such an effect is observed. So, these capacitors actually are the reasons for the response curve trend that we get in single stage amplifier. Let us see how this alters the trend. It is clear that the voltage gain drops off at low frequencies, which is less than the FL, lower cutoff frequency, and high frequency, that is FU, greater than FU, where as it is uniform over the mid frequency range, that is between the FL and FU. The analysis is done normally by a theorem called Miller's theorem, but the theorem is beyond the scope. So, let us see a simple explanation here. As I said, this is the frequency response curve which I wanted to show in the beginning of the lecture itself, but nevertheless we have the trend here shown. This is the lower frequency region, higher frequency region, or we call it as upper frequency region, and in between we have the bandwidth. And in this lecture we have to find the reason for taking bandwidth with respect to the mid frequency region with respect to the off power gain line. At low frequencies, the gain slowly starts increasing when the frequency increases, and the case is just the opposite in the case of higher frequency range, and in the mid frequency it is maintained more or less constant. So, the effects are like in the lower range there is one reason, and for the higher frequency region the reverse is the reason, and in the mid frequency region one effect is cancelling the other effect. This is what we could understand at a basic level. As I said, the capacitors have their own effects in allowing the frequency of the signal into the circuit. Let us see how the two capacitors do behave for various frequencies that we give. At low frequency, the reactance of the coupling capacitor is quite high, and hence very small part of the signal will pass from the amplifier stage to the load. Moreover, capacitor connected across the emitter, which is called CE, cannot shunt the RE effectively because of its large reactance at low frequencies. These two factors cause a falling of voltage gain at low frequency. So, we have seen the reason. It is mainly due to the external capacitors we connect to the circuit. We have three capacitors connected in the single stage amplifier. One is the base capacitor, the other one is the emitter capacitor, the other one is the collector capacitor. The base capacitor is confining the DC into the stage, and similarly the collector capacitor also. But the emitter capacitor produces a kind of stability to the circuit. But here the capacitor which is on the input side and the capacitor which is connected across the emitter, they offer a huge reactance when the frequency falls, when it is low. So, that is why it is affecting the gain very much. Now, let us see what is happening in the other frequency ranges. What is the reason for the frequency response curve? At high frequency, the reactance of coupling capacitor C is very small and it behaves as a short circuit. This increases the loading effect of the amplifier stage and serves to reduce the voltage gain. For the response we have for the high frequency range, again the coupling capacitor is the reason, and here the reactance is different and it is increasing it is again reducing the gain when the frequency keeps increasing. So, we are confining our discussion with respect to the external resistors that are used in the circuit, and we do not take the internal resistors very much because, as I said, we need to use the theorem, Miller's theorem, for understanding the behavior of the internal capacitors considered across the two junctions. They too also have an effect on deciding the trend of the graph. Now, we will find out what is the reason for the behavior in the mid frequency range. Moreover, at high frequency, the capacitive reactance of the base emitter junction is very low, which increases the base current. These reduce the current amplification factor beta. Due to these two reasons, the voltage gain drops off at high frequency. We have indeed considered the internal capacitor playing a role in controlling the gain at the high frequency. Capacitor has an effect. We will continue our discussion further after a short break. Welcome back. At high frequency, the capacitive reactance of the base emitter capacitor that is developed across the junction, that is also playing a role. Because of that, the gain decreases very much when the frequency increases. Now, it is time for us to see the reason for the behavior at the mid frequency range. At mid frequency, that is from the lower cutoff frequency to upper cutoff frequency FL to FU, the voltage gain is constant. The effect of coupling capacitor C in this frequency range is such as to maintain a uniform voltage gain. In mid frequency range, the reactance of coupling capacitor C decreases and the gain increases. On the other hand, due to the low capacitive reactance, there will be higher loading effect on and gain will be reduced. As the two different effects neutralize each other, hence the gain is constant in the mid frequency range of the amplifier. So, as we guessed earlier, in the mid frequency range the gain remains constant because the two effects, the low frequency effect and also the high frequency effect due to the capacitors, cancel each other reasonably in the mid frequency range. So, the gain is more or less constant. We can understand the behavior with a elaborate discussion made with the help of Miller's theorem. That discussion is of high level, it is beyond the scope of this course. So, that analysis is not taken up for discussion here, but we have taken up the change that is happening with respect to the capacitors and the reactance. These are alone considered for giving the reason for the behavior of the frequency response of the single stage amplifier. So, we have got now an idea, some sort of basic idea, the reason for the behavior of the frequency response curve in the case of single stage amplifier. Think for this course, this explanation is sufficient. Now, one more thing with respect to the frequency response curve we need to take up for discussion. It is the half power gain that we consider for taking the bandwidth. Why do we have to consider a term bandwidth? Can't we take the mid frequency range as the preferred range for using the amplifier? The trend of the graph that I have shown is just a model. It is not the practical response curve. When we take a practical response curve, the bandwidth sometimes would not be of this much long, it would not be of this long range, very extended range we have seen in the graph which I have shown, but it would not be of the same big long range. In that case, the range of operation where the gain remains constant is very much reduced. It depends on the components that we use for designing the single stage amplifier. In that case, how do we have to have a reasonable range for the mid frequency range, the range which is called the mid frequency range? Let us have a look at the trend of the graph once again. With the graph, I will be able to explain you the bandwidth and why do we have to consider half power gain line. See here, this is the mid frequency range as far as the frequency part is considered, without considering the half power gain line. But when we are ready to lose the gain by a value, because of the trend that we have, the frequency range is getting extended. When we consider this as the reference line, the reference line cuts the graph at the 2 points, which is greater than the mid frequency which is marked here, keeping only the frequency in mind. So, the bandwidth is extended. See here, on either side it is extended. So, it is better to lose some gain in order to get the extended range for the bandwidth. We need to operate the single stage amplifier mainly with a constant gain. That was the aim. We need to have a reasonably constant gain. So, we want a extended range of frequency so that reasonably the bandwidth is sufficient for its operation, because we may have to amplify a vast range of frequency signals. So, we need to have an increased bandwidth. So, it is better to sacrifice some amount of gain. How much we need to sacrifice, how much we are ready to lose the gain in order to get the increase in bandwidth. So, here comes the half power gain line. If we at least get half of the power as the output of the maximum, then that would be reasonable for us to have the increased bandwidth. This is the idea. Then why the root 2 in the denominator? That is the main explanation we need to get. So, let us have the explanation for taking the root 2 in the denominator. Whenever we say half, the term 1 divided by 2 only comes to our mind. We need to divide something by 2, then it is half. But half power, when we say, we are dividing it with the root 2. Why root 2? We will get the explanation now. The half power point of an electronic amplifier stage is that frequency at which the output power has dropped to half of its mid-band value. The level is marked as 1 divided by root 2, which is 0.707. In decibel, when we want to mention that, it is reduction in the value, so it is minus 3 dB. The half power point is a commonly used point as a specific definition of cutoff frequency. In the current electricity, power is proportional to the square of the current or the square of voltage. So, it is shown within bracket I square or V square. Shall we recall to our mind the expression we have for power? It is nothing but the product of current and voltage. V multiplied with I is power. When you want to write it in terms of either the current or the voltage alone, then it is I square R or V square divided by R. These are the two expressions we use in electronic circuits for power. This concept we have already learnt when we learnt the electricity in one of the earlier lectures. So, I have not given the elaborate expressions for the power, it is already learnt. So, we know now it is proportional to I square or V square. When we want to reduce the power to half, then what is to be done? We need to reduce either the current or the voltage only in the case of reducing it by half. So, how much we should reduce when it is in the square proportionality? That is why the root 2 comes. Let us see the expressions for it. To reduce the power by half, the current or voltage has to be reduced by the root 2 value, because already I square or V square are in the numerator. So, if we reduce the I value divided by root 2 or V value by root 2, then the whole value, the power will be reduced by half. Hence, the root 2 comes. So, 1 divided by root 2 is shown here as a value, which is numerically equal to 0.707. So, that is why we take the half power gain line at a value of gain which is reduced by root 2. It is divided by root 2. As I said, the frequency response curve gives us lot of information about the range in which the single stage amplifier could be used. When we design the amplifier by considering the biasing and the capacitance value, and of course, the typical amplification factor beta of the transistor, we will get different trends, but all the trends will be the trend here I mean is the frequency response curve. All the trends will be of similar in nature with the lower cutoff frequency, upper cutoff frequency and mid frequency ranges. All the trend will be the same. But how do we get an increased bandwidth? So, as I said, the gain is to be sacrificed for getting the increased bandwidth. In the design aspect itself, we can have a control over choosing the bandwidth. Nevertheless, in the consideration of the frequency response curve, so customarily we draw a line at the half power gain point and then take the bandwidth. Just now I have just mentioned the beta value. How do we get the beta value for a transistor? It is provided by the manufacturer. What are the other factors which are available when we commercially get a transistor? There are a lot of factors we get along with the transistor. The manufacturer would give them as specification: the input resistance, the output resistance, voltage gain and the current gain. These are the 4 parameters normally we get when we purchase a transistor. These factors are very much useful in designing the transistor circuit. So, in the subsequent lecture, I will be able to explain to you what are the different parameters we could consider in the case of a transistor, especially a term called H parameter. The next whole lecture I would like to devote for the H parameter. We will have a different approach on the operation of a transistor. There we will give much importance to the mathematical analysis of the circuit. So, I reserve the topic H parameter for the next lecture. So, let us recall to our mind what are the topics we have seen today. We have got the information, especially the reason for the behavior of the amplifier for different frequency ranges. So, let us see today's session summary. In this session, we have seen concepts related to single stage amplifier, the reason for the frequency response and also the reason for taking the half power gain line as the reference line for deciding the bandwidth. Before we wind up the lecture, let us test our understanding by answering these questions. Explain the reason for the trend of frequency response curve in the low frequency, mid frequency and high frequency ranges. Explain why we take the cutoff frequencies at half power gain line. With this, I wind up today's lecture. See you in the next lecture with the concept H parameter. Thank you.